the previous video, I introduced the second law of thermodynamics, and we talked mostly about the dq over temperature terms. In this video, I want to focus more on the new terms that have been introduced in the second law of thermodynamics, specifically the delta S and the S-gen term. So on the left-hand side of the second law, we have a delta S, and what this delta S is describing is it describes the change in entropy of a system. Okay? And our delta S itself can be positive, negative, or 0. And so essentially the system can either increase the amount of entropy it has, it could decrease the amount of entropy it has, or the amount of entropy it has over the course of a process can remain the same. Okay? And so this is specifically talking about the entropy of the system. Right? Another way to articulate this, or another property of entropy, is that delta S is a state variable. Right? And so it's only going to depend on the endpoints. Okay? All right, and so the idea behind this, I could give you an example, is that if we think about that isothermal reversible expansion, I showed that the delta S was equal to nR natural log of volume 2 over volume 1. Okay? All right, and so these things are constants, and so the volume terms determine what our delta S is going to be. And so if we undergo that reversible isothermal expansion, where we go from some initial state to a final state, and then return back to that initial state, what we would have is that our delta S, we would be integrating it from volume 1 to volume 1, nR dV over V. Right? And since the endpoints of this integral are the exact same, what we would get back out is that the change in entropy of our system would be equal to 0. Okay? And so that's what I mean by state variable, is that your delta S only is affected by whatever the properties of the initial and final state are. It doesn't matter how it gets to those initial and final states. Okay, so that's delta S. Ooh. The next thing I want to talk about is S-gen. Okay? And so this is the entropy generated. S-gen is the entropy generated by the system. Okay? And to relate this back to our previous discussion about heat engines, this S-gen, you could think of it as the heat lost by the system divided by temperature. Right? And so if we put heat into the system to create work, not all of it, in an irreversible process, not all of that heat gets converted into work. Some of it is lost, and our S-gen is essentially that lost heat divided by whatever the temperature is of the system. Okay? All right, and another way to at least kind of give somewhat of a physical meaning to S-gen is we could think about it in terms of work, more directly in terms of work, right? And so if we say that work reversible is the hypothetical maximum amount of work that the heat engine can produce, or the process can produce. If we look at the differential forms, we know that in the case of the irreversible process, the amount of work we get out of it is less than the reversible process. Okay? And if we take d reversible and subtract off d irreversible and divide it by temperature, that would be equal to dq lost. That difference between the works there would be equal to dq lost, right? And this heat is lost to the surroundings. Okay? So dq lost is basically the difference in the work that we could extract from the reversible process and the irreversible process. And if we take that dq lost and divide it by temperature, that's essentially what we're calling dsgen. Okay? And so Sgen is the entropy generated by the system. Okay? And delta S is the entropy change of the system as well. Okay? All right, so I talked specifically about the system, but more generally, we also need to think about the change in entropy of the universe. Okay? And so the change in entropy of a universe when a process occurs is going to be equal to the change in entropy of the system plus the change in entropy of the surroundings. Okay? And this change in entropy of the universe, if we account for both the system and the surroundings, the way to think about this is, what is the entropy generated within the universe? Okay? And the reason I put it like that is because when we talk about Sgen and Sgen of the universe, these things can never be negative. Right? So even going back to here, when we think about reversible work and irreversible work and the difference between the two, this difference can't be negative. Reversible work is always going to be greater than the irreversible work. Okay? And so for that same reason, the entropy generated by the system or the universe, they can't be negative, right? They could either be positive if you have an irreversible process or 0 if you have a reversible process. Okay? Another way to say that is that the system and universe cannot consume entropy. Right? You could either conserve it or you could generate it, but never consume. Okay? All right? And so at least, when discussing what delta S and Sgen are, for now I kind of just focused on, what they mean mathematically. But more importantly, we need to talk about what entropy means physically. What does it physically mean to increase the entropy in a system or decrease it? But to do that, to at least get a good handle on what entropy means, we're going to have to wait a little bit. Because for right now, we don't have the mathematical tools. I haven't introduced yet the mathematical tools needed in order to have that discussion. Okay? But I'll at least just kind of tell you that to define what entropy physically means, we're going to have to wait until we get to chapters 6. But earlier than that, get to what I call chapter 5.5. Okay. So we'll leave that for later. But at least in chapter 4, we can at least learn how we could apply the second law of thermodynamics to help us understand our chemical processes more deeply.